Well, hello guys and welcome back to the channel. Today I want to show you this node group that I created. It creates an offset of a curve or even of a mesh. It needs to be 2D, but still it creates an offset. That's something that innate Blender geometry nodes do not have. So it's something I think it's pretty cool for a lot of uses. You can obviously watch me recreate this node group with you and you can make your own, or you can, as usual, download it from the link in the description. It's only $2 and it would be a way for you to support this channel. And of course, maybe you don't like to spend time watching me explain all this stuff and to recreate this node yourself, so maybe it's easier for you just to download it and use it. Anyway, first part of the video I'm going to show you how it works, and the second part of the video we're going to go through all of these nodes that recreate this offset behavior. So it's a simple node, looks like this. You can connect it to your geometry. So here we have a polyline curve, here we have a Bezier open curve, and here we have a Bezier closed curve. Here we have a plane, and here we have a simple cube. All of them have applied this test, I call it node. This actually just geometry group output and input within the middle this offset node. So here is how it works. Here we have, so let's just mute it so you can see what it looks like. It's a polyline curve, and if we unmute it, you can see that here is the offset distance that controls the offset or the inset. It creates, let's say, a duplicate of the curve, and it insets it or it offsets it. And this one works fine for these kind of curves. Here we have a different one. This one is, okay, let's just change this to the test thing. Okay, here we have the same group, and as you can see, with this Bezier curve, it doesn't work as it should. Why? Because as you will see in the explanation, this offset group uses the position of the control points or the vertex points to construct the offset. And here, as you can see, if we go into our edit mode, here we have only 3 control points, and these do get offset, but the result is not as it should. But we have a solution for this. We just need to resample the curve in these cases. So if we resample the curve, and then we can set the resolution of the curve, so these are the vertices that we're going to use for the curve, and then we have the wanted and expected behavior. Perfect. The same thing goes for this closed. As you can see, if we don't resample the curve, weird thing happened, but if we resample it and that's set, and then set the vertex resolution, the number of vertices to our likings, we get the wanted result. Perfect. Then we have the plane. As you can see, the plane happens, nothing happens to the plane, obviously, because it's a plane, regardless of the resampling or not. But there is another checkbox here that we can check and it will do the job. Then meshed curve, so we can convert our mesh, in this case our plane, into a curve, and then it will work fine. Here we go. You lose a face, but for now this is the best we can do with this. And then we have our cube. As you can see, nothing really happens with the cube because this is only for 2D curves and objects. So if we convert it to a curve from a mesh, it will still do nothing. So this is only to show you that 3D does not work, as you would probably guess yourself, because offset is a 2D operation. And but we can use this object to connect maybe a quadrilateral. And here we don't need this. As you can see, you can connect whatever you want in this and it will work regardlessly. So you can use this node in a whole different and much elaborated node tree. Okay, so now let's begin diving into our group nodes. Here I set up these output attributes that will help me explain what I actually did. So this is actually minus these two. This is actually the group node, and this is just something that I want to plug into it. But this here is the group node. So we're going to explain it here. This is just geometry. This is what comes out of it. This is just simple. I don't know what we got here. We got a circle, and maybe we want to scale it on an axis, and maybe we want resolution. I don't know, maybe we want 4 vertices for now. And let's just get rid of this because they get in the way. Delete, we don't need that. Okay, so bear with me. We're gonna leave Blender for just a second, and we're gonna go into AutoCAD to show you how the math and the geometry behind all this. So I want to show you what's behind this construction of the offset. So here we have a triangle and an hypothetical offset by the value t. So all these lines are parallel to all the other lines, and so they are all distance the same t value. But as you can see, this c value is the distance from the points of the original shape. And as you can see, these c values are all different. So this one is 3.2, this one is 3.5, and this one is even bigger, it's 4.9. So how can we construct the new offset shape if we only know the position of our vertices, right? We know the normals of our vertices, and the normals are actually the angle bisector, but the inverse angle bisector. So the normals face outwards. This is the normal of this B point, and the normal of the C point would go somewhere over there. So we know the position of our vertices, we know the normal, and we know the t value because that's the value that we set. That's the offset that we want to set. So how can we find out the c? C in this case can be found out with this operation. So sine of omega, this is this angle here, is equal to t divided by c. But we don't have the omega angle. But what we do have, anyway, when we get the sine of the omega, we can find out the c pretty easily. But what we do have, we have the vertex of the normal, and we have the position of a vertex, but also the b vertex, and also the c vertex, and whatever. So we can actually find the vector of the AB segment. There is a math operation, math formula to do that. But anyway, so we can find this vector, and we can find the inverse vector of the normal. So we will have this vector, and we will have this vector, and then there is also another mathematical formula to find out the exact value of an angle between two vectors. And once we have an angle and we have t, which is a value that we set, we can calculate the c. So this is the formula for calculating a vector given by 2 points, the a and b in our case. Pretty simple. And this is a little bit more complicated, but still it's a mathematical formula to calculate an angle between two vectors. You need to calculate the magnitude of both vectors. So the magnitude of vector A is square root of x component squared plus y component squared. The magnitude of B is the same thing, and we need to calculate the dot product of the two vectors, which is given by this formula. And then the cosine of omega would be the dot product divided by the product of the two magnitudes, and then the measurement of the omega in radians would be the arc cosine of our angles. And then once we have the omega, we can use this formula to calculate the C, and this C value will be in respect of all the different vertices. So here we're gonna need the T is always the same, but here we're gonna need this vertex, so B, I don't know, C segment, and here we're gonna need our CA segment. And for all the vertices of our curve, we're gonna do the same thing. So we're gonna look at the next vertex in line, we're gonna calculate that vector, and then all the other stuff that we went through. So let's go back to Blender and let's see what we've done. Okay, so here we have our scaled square, and now first we need to find, let's just open this a bit. We need to find, so these are our vertices, the position, the coordinates of our vertices, and we need to find the coordinates of the next point. So for the vertex ID'd as 0, we need to find coordinates of the next vertex in line. For number 1, we need to find the next here, and for this next. So everything is already here, but we need to place it, let's say, on the right line. So this values here need to be connected to these values somehow. So in the old attribute version of Blender, the geometry nodes, before the fields, we would add an attribute and then it would be here. But now we do it a little bit different. So we need to transfer the attribute or capture the attribute, but we use the transfer attribute here. So we plug in this geometry. So this geometry here, these vertices, gets plugged in here, and we need to transfer what attribute? The position attribute of what index. So this is the index, and we add 1 to each index, and then we look for the position of that index, and then we connect it to this one. It's a bit complicated, but so I connected this output of this transfer attribute here, down here, so we can have a better control of what happens to this position B. So here position B, let's just say plus B, and here it is, and now it's connected. So what I've done here, so I've said, okay, we have this vertex 0, and let's see what the position value of a vertex 0 plus 1 is. And it's actually this right here. For this, it's the next one, as you can see. So these values are these values, these values are these values. Where it gets interesting is the last vertex. So the last vertex, as you can see, this one in our case, because here we have only 3, needs to have the first vertex as a reference to create that vector point. So we need to somehow connect this one to the 0, and we use this modulo operation. This is a math node with the modulo operation. Modulo operation gets the value here, let's just place 3, the value here gets divided by this value, and it brings out the result of this operation is the rest. So 4 divided by 4 is 1 with the rest of 0. 5 divided by 4 is 1 with the rest of 1. And so the result would be the rest. So what remains out of the divided operation to have like a full integer number. And so we need to plug in, and so this is the number with which we divide this value. So we need to plug in the resolution, which is in our case the number of vertices, so that we divide it by the number of vertices. So in our case we have now 5 vertices, but this is ID'd 4. So 4, you add 1, now you get 5. So you get 5 divided by 4, divided by 5, sorry. Divided by 5, you get 1 and the rest of 0. And so here it comes out 0, and so it looks at the index of 0. And that's how you do the loop thing. That's how you do the loop thing, and you get this value that you wanted. This value is this value. Okay. We are losing so much time, but I don't know how to explain it in a more in faster way and still to be kind of understandable for everyone. Okay, so now we have this position B vertex connected to the same line of the ID vertex. So we have position A, position B. Here we have position B, position C. So these are the points, these are the copies, pairs of points. So this and this, this and this, this and this. And what we need to do now, we need to find a vector passing through these 2 points. And that's simple. You have a math operation, already told you, it's this one here. You have 2 points, and this is the operation to find a vector. Let's go back, and that's exactly what I've done. So we have a position attribute and our new transfer attribute position B, this one here. We just subtract the 2, and the result that I also plugged in here is vector AB. Vec AB, let's call it. And here we have the vector AB still connected to the right ID. Okay, so now we have a vector AB, and we need the normal, inverse normal, to get these 2 vectors and find the angle between them. So the inverse normal is just your vector multiplied by -1, and this vector we already found its dimension. So we have the normal multiplied by -1, we get the inverse normal right here. Inverse normal, let's call it N, and here it is. Let's just move everything a bit here. So we have vector AB and vector inverse normal, and between these 2 vectors there is an omega angle that we need to calculate. And this is where it gets complicated with the math, but it's just math, nothing to be scared of. It's all here, and that's what actually happened here. So we have vector normal, the vector, the inverse vector, and the AB vector. Here we separated the components into x and y here, into x and y here. The z is not relevant because we are facing and we are dealing with 2D curves, and then a lot of math. So here we have our dot product, and here we have our magnitude of the one vector and the magnitude of our second vector. They get multiplied here, and now we need to divide the dot product with the magnitude, with the product of the 2 magnitudes, and we got the cosine. With the arc cosine, we get the value of the angle in radians, 2 degrees, and it gets out as the angle in degrees, and here it is, omega. So let's call it omega, and let's see it right here. So this is the omega here, right here. So 68 angles. Remember, these are the angles we are looking for. So the angle bisector here, this is the omega for vertex A. The angle bisector here, this is the omega, because this is the vertices we are controlling for this point. And also, again, the angle bisector, this is the omega for this vertex. And maybe we can I believe this is the correct value. As you can see, it's around more than 68 here. This is around 40, and this is around 60, so it kind of looks okay. We can even check it out and test it if we set this scale to 1 and we have a perfect pentagon. So all these angles, angle bisector, remember pentagon has I don't know how much pentagon has, but let's set a hexagon. We know hexagon is 120 degrees and the angle bisector gives us 60, so you can see that the calculations are correct. Okay, so now what we have the angle of omega, and we go back to our formula here, and now we can calculate the C. So now let's go back again. Distance, this distance here is the offset, is the value of the offset, and we need to plug and divide by the sign that we need to switch back to radians. Okay, anyway, here we got the t value. So the distance, not the t value, sorry, the c value. Is it the c? Yeah, the c value is here, and I plugged it here. It's not t, it's c, but anyway, it's c value, and we have it here. Okay, so it depends on this distance. So as I move this distance, as you can see here, the c value is always the same, because let me just connect the end one to here. So you can see that the offset is always, since this is a symmetrical curve, you can see that the c in this case is always the same value. But what happens if I scale it on this axis, for example? And here you can see that this value here, maybe this is not a good example, let's just do like this, okay, also here in this example, you can see that this dimension and this are two very different dimensions, and you can see here, so these bigger ones are 1.8 and the little one here is 0.4. Okay, so how did I, once that you get the c value, that's here, how do you use it to move your vertex to that position? As you know, we have a position vector, we have the normal vector, so we also have the inverse normal, and we need to move this point in the direction of the normal by adding it the value c. So this is how you do it. You just use your set position node, you plug in your position, and you use your position value, so this is the position of that vector, and you add to it a normal, an inverse normal. This is an inverse normal. You separated the inverse normal, and you multiply your inverse normal coordinate, you multiply it by the value c, that is this one. So the x component gets multiplied by the value C, and the Y component gets multiplied by value C, and it all gets added to the position. And that is it. And then it all comes out. So I joined the original geometry with this offset geometry, and this is the result I get. That is it. So guys, a little bit of a long video, but it is kind of complicated to do, and hopefully you'll be able to recreate this node yourselves. If not, there's always the option to download this node from the link in the description. It's not free, it's $2, but it's a way to support this channel and my work on this channel. So thank you very much for watching, and I will see you in the next one. Bye bye.